Okay, our next speaker is Håkon Gylterud, he will talk about univalent set theories.
Thank you, Christian. So I wanted to give a talk about something which Eric might enjoy, and therefore I chose to talk about something which I started on during my PhD thesis. And I wanted to say a few words of how it was, how this came about because of Eric, and how Eric was a very patient advisor. I would his way of advising me was that I would every once in a while come to his office and just pour my ideas out on the board, and he would comment and give references to things which were relevant and so on. And he was very patient with my ideas. He never said a bad word about any of them, even though a lot of them were unfinished or confused or a lot of things. But in one instance, he really, well, to be Eric, at least, he really got excited about what I was presenting. And that led me to work on this. So I don't remember where I first encountered Axel's model of set theory in type theory, but I think it was Eric who presented it to me at some point. And on a whim, I decided, okay, let me compute the identity type of this using the univalence axiom. We can now compute the identity type on the universe, so we can compute the identity type on Axel's model, which Nicola presented just now. So because the type is a W type based on the universe, we can compute the identity type. So I did that sort of on a whim, and when I presented this to Eric, he was quite excited and happy to see that this homotopy type theory could shed some light on Axel's model. By him being, so if he hadn't been excited, and by excited I mean he smiled and said something like, that was interesting. But if he hadn't been excited about it, I would probably have discarded the whole thing, and most of my PhD thesis would not have come about. So today's talk is titled Univalent Set Theory, and I hope you can all see the slides now. And I hope to convince you that set theory is not something which only happens on set level 0. So I want to sort of separate two different aspects of set theory. And I think of set theory maybe a bit differently than it's often presented. I've come to think of set theory as a kind of mathematics, like group theory. It's something we do inside type theory, which is the meta theory. And we think of set theory as another kind of mathematics, which we do inside type theory. And that sort of separates the two aspects of set theory. The set theory, which has to do with where the end product is that we create the category of sets, where we can do all kinds of useful constructions for doing algebra and other things. And then there's, to contrast, there's this other aspect of set theory, which is the iterative aspect, where we have sets which are elements in sets, which are elements in sets, and so on. And so when it comes to the creating the category of sets aspect of it, that's perfectly well captured by H sets in homotopy type theory. But this iterative aspect, what I'm trying to put forward today here is the idea that that aspect is not limited to H level 0. That's something which could happen on any H level. And the axioms of constructive set theory can be extended to say something meaningful also for higher H levels. So this was work which I started in my PhD. So references for this is my PhD. But in my PhD thesis, I sort of took this all the way from being from H levels to going directly to the infinite level. And in this talk, I want to interpolate a bit between those and talk about each H level separately. So when we start saying what a model of set theory is, or an elementhood structure, as I would like to call them, the usual setup is that we have an underlying H set, which is the type of all sets, and then we have a predicate on this. And what we're doing is that we're crossing out H set and prop and putting type and type. But that doesn't mean we're back to Axel's interpreting things as setoids, because we will still use the identity type on these. So we'll use the identity type as the equality, but we'll not restrict the type levels so that they are on H sets and props anymore. And in between H sets and general types, we can interpret a structure on each level. So an elementhood structure on level n+1 consists of an n+1 type V and a type family over that with 2 arguments, which lands in n types. So we see that there's a shift here where the underlying type lies in this type +1. And it should satisfy something I've called set univalence, which is set extensionality, but lifted. And I'll explain that in a moment, what that is. But an example of such a structure is the V from the hotbook, which is then at level 0. And I wanted to give 2 more examples before I tell you what set univalence is. But the first example is just that we take Axel's type, this W type, where we have all well-founded trees which are branched in, with the branching sets being in the universe, and the elementhood relation is defined, well, as the immediate subtree relation. So we have subtrees, the subtrees of the larger tree are its elements that we could formulate if we look at W types. They are essentially pairs, a type of branchings, and an F which assigns to each branch the element there. So the elementhood relation is the inverse, the H fiber over that point. And then there's also the dual of this, where we, instead of the W type, take the M type, and we can similarly there define elementhood in the same way. And these are structures on the level infinite. So these have no H level restrictions on them. And then the question I wanted to address a bit today is what is between level 0 and infinite. And we'll consider a hierarchy of models, which is very much like the one Nicola mentioned by Cesare, but it's slightly different. So we'll get back to how it's different in a moment. But I also wanted to say something about how do we interpret this elementhood relation when it's no longer just a proposition. So when it's just a proposition, elements are either there or they're not, so to say. They're at most one time. But if it's, let's say it's a 0 type, then we can have one element occurring more than once in the set. So it's like a multiset. And then as we go into higher dimensions, we have higher types of occurrences. And that's a bit difficult to get one's mind about. And so my difficulty with understanding that is what leads to what comes after. So, but first, set the extensionality. So we want to rephrase all the axioms so that they fit also for these higher structures. And we start with extensionality, because that's the foundation upon which we build all this. And remember that set the extensionality says that two sets are the same if they have the same elements. if you write that out in logic, it becomes a formula like this, where we have, if for all z, z is in x, if and only if z is in y, then x equals y. And the other direction is trivial. So it holds in any structure because equality is the least reflexive relation. And so the implication in the other direction always holds. And that's how we will start to generalize this, namely by taking, when we lift it up to any level, then we have a function going from x equals y, which is this is the trivial implication, into the product over all z in v, z is an x, and then we put type equivalence because this doesn't have to be something of proposition. So by implication is no longer the right notion of equivalence. So we lift it to equivalence. So z is in x is equivalent to z is in y. So there's a function going there, which takes the reflexivity proof here to the identity equivalence. So if x and y are the same, then we can have the identity equivalence here. This holds trivially in any structure. And then in a complete analogy with univalence for types, we say that set univalence is the fact, or the requirement that this is an equivalence. So in the structures we consider, we will consider those for which this is an equivalence. And we see that if we go to the structures which are on level 0, then this specializes exactly to the usual extensionality axiom, because then this is a proposition, and this is a proposition, and this is a proposition. So this is just by implication, and the fact that this is an equivalence just means that we have an arrow in the other direction. So that's set univalence, and we see that this generalizes set extensionality to higher levels. And now we want to do the same thing for different axioms of set theory, but first I wanted to present two hierarchies which sort of interpolate between this ground level normal everyday interpretation of set theory in hot towards this underlying type of the axle at the top. So we start out with axle's type, the W overall A in U A. So that's all well-founded trees. And we say that well-founded tree is an iterative n+1 type if, and then we define this inductively, the f, the function which picks out the subtrees, is n-truncated. And why do we have n-truncated here? Well, n-truncated means that the H fibers are n-types. So this means that when we defined elementhood as the H fibers of F, so elementhood, so that F is n-truncated is exactly that the elementhood relation is an n-type. That's the reason why we have this in the beginning here. We have V is an n+1 type, and the elementhood relation lies on n. That's because when the elementhood relation here lies on some H level, then we know also the H level of the equality here. So this turns, so this is why this is now an n+1 type. And then this should hold iteratively for all the elements and the elements of the elements and the elements of the elements and the elements of the elements and so on, all the way down. And then we define Vn, the model on level n, to be all the elements which are iterative n types.
Can I interrupt you and say I still haven't grasped your generalization of extensionality?
Okay. Shall we go back to it? And Do you have a concrete question, or?
You seem to well, so I can see you have the trivial direction there, and
yeah.
I don't grasp what the non-trivial direction is.
Oh, the requirement is that we have an elementhood relation which satisfies the requirement that this trivial, the arrow in the trivial direction, is an equivalence.
I was hoping for more explanation of the consequence of that.
So one of the consequences of this means that we can more or less compute the identity on V from this because we can it is determined by the elementhood relation. So the identity type on V should be determined by the epsilon relation in the same way which the identity type on the universe is determined by equivalences.
Can I ask a question?
If I may add. Sorry, I think I am someone else. If I might just very quickly add. So I guess the first consequence of saying that the non-trivial direction is an equivalence is saying saying that the trivial direction is an equivalence implies immediately that the non-trivial direction holds as well. May have been part of what I was asking.
Okay.
Well, no, I wanted to push it a bit further because I know that the extensionality axiom makes the epsilon structures very rigid. They don't have any non-trivial isomorphisms or automorphisms or isomorphisms amongst themselves. And I just wondering whether you could say more on the consequences, but if not, just carry on.
I'm not sure I understand the question quite, so I'll carry on.
Could I ask a quick question while we're asking you?
Yeah, sure.
Håkon. So do you know whether there's any analog of the Mostovsky collapse? Can you turn something that's not set univalent into something that is set univalent in some way?
I don't know. I haven't thought about that question. I haven't thought about the Mostovsky collapse in this.
That's what Håkon does in his thesis, isn't it? The Mostovsky collapse is the quotient, and what you do is carve out a subtype that's equivalent to the quotient by the composition. Isn't that right?
Yeah, so I think the Mostovsky collapse here would be, if we look at the models, let's see. So we see here that the top model, the one at level infinite, it is the it's the initial algebra, so to say, for the polynomial functor, which sends x to the sum over all a in u x to the a, and I think the Mostovsky collapse has something to do with the fact that this is also then a coalgebra because it's the initial algebra, but I'm not quite sure. Yeah.
Okay, can I come back in on that one? Mm-hmm. What I was hoping for is an answer to my question about meaning of extensionality is that in applications of homotopy type theory to other topics, like groups, for example, people have demonstrated that univalence gives rise instantiates to some well-known principle, and I was hoping that you might say something similar about set theory, but if not, then we should proceed. Now, asking about the Mostovsky collapse, I suspect, is a much more difficult question that we should leave to the end of the talk.
All right. So where were we? Oh yeah, so we have defined extensionality to be the fact that this this function is an equivalence, and we can prove that for the models we have here, and thus they hold also for these submodels. But we define this to be an iterative n-type, exactly so that the elementhood lands on the n-1 level. And thus, by extensionality, we can compute the level of each of these to be exactly n, so of these types. And elementhood is then defined. These are all well-founded trees, and they all have the same elementhood relation. And then there's a dual to this, where we, instead of taking inductively the n-truncated trees, we take co-inductively the n-truncated trees, and we can define the co-inductive models. And then we'll look at other axioms. Maybe when I present a few more of these axioms, the general way of translating these axioms become more clear and perhaps more understandable. So first one out is separation. So an elementhood structure has n separation if for every n-truncated predicate. So that means that you have a function from v into u, where it's n-truncated on every point, and you have some specific a in v. Then there is a set, which is the separation of a with respect to that predicate v, and it has the property that set is in this set is equivalent to set is being an element of A multiplied by the predicate. And this is sort of general how we deal with set extensionality. With set existence axioms, it's that we characterize the elementhood relation on that set up to equivalence, and that uniquely determines the set by extensionality. So the univalence axiom for these sets give us that this completely characterizes the set. And another example is unordered tuples. So we say that an elementhood structure has n unordered tuples if for every k and every choice of k elements in V, there is a pairing or of those such that being an element in that pair is equivalent to their existing an I such that Pi is that set, and then we n-truncate that. And if we don't write anything, we assume that n is infinite and we don't truncate. And the reason here that we do all tupling at the same time, not taking just the empty set and then pairing, is that multiplicities count. So you can't do the usual trick of defining singletons, for instance, as the element paired as it's with itself. So I have a slide elaborating on that. So for instance, y being an element in the singleton, if we don't truncate, is as a type. So this is a type, and that type is exactly equal to the identity type between x and y in V. So for instance, if we take x as an element in the singleton x, that's exactly the type of automorphisms of x in V. And this is not always contractible. But if we want that to be a contractible type, we can take the -1 pairing instead, or the -1 tupling instead, and take X is an element in the singleton truncated, and that will be then contractible. Similarly, if we take X is an element in XX 0 truncated, so that truncates the elemented relation to a set, that will have exactly 2 elements. So this will be the type with 2 elements, which sort of can be interpreted as X occur twice in this set. Then we have, for comparison, if we didn't 0 truncate that, then that would be the disjoint union of X equals to X and X equals to X, the identity type. V minus 1, so that's basically the hot model, the hot book model. It has only -1 unordered tuples, and that is because this is a finite set. It's a 0 type, not a -1 type. But all the higher V's have k unordered triples for all k, so they have these at all levels. Then there is sort of a demonstration here that higher groupoids show up, or at least groupoids in the first. So for instance, if you take all the X's in V, which are elements in this here, so this is the -1 truncated singleton of 0 truncated pair of the empty set and the empty set, then that will be the groupoid Z2. And why is that? Well, that's because being an element here, so this is a proposition, so this doesn't really count when we're computing the identity type of this. So the automorphisms of this is automorphisms of the single element here. So that's this equal to this, which is then by set extensionality is the product over all V. Set is in V is an element of this equal itself. And by the previous slide here, we had that being an element in the pairing XX is the same as 2. So this is 2 equals 2, which is exactly this groupoid when set 2, because that's the automorphisms of 2 elements in the universe. So it's very easy. Even just using pairing, you can get things with higher homotopy structures here. And then ordered tuples, that's not an axiom, that's a structure you can put. And it's the kind of obvious definition is that you take an ordered tuple structure to be an embedding, in the sense of hot, of Vn into V. And here we can use, this can be encoded in different ways, but we cannot use Kuratowski's encoding because that doesn't work for any levels above -1. But you can use, that has to do with how Kuratowski's sets are chosen very minimally, and the first element of the ordered pair occurs twice in a way which adds up to, when you look at the identity type on that, it adds up to getting not the right identity type. But Norbert Wiener, who was actually the first one to define such a pairing, he had a definition which works also for all higher types.
Can you tell us what these encodings are? Because my understanding was these were the same thing.
Oh yeah, sure. Let me find something to write on. One moment. Oh.
I think you can Google that.
Hmm?
You can Google it.
Yeah, that he could. I could also write them in. Yeah. So Peter has the link.
I've posted in the chat.
In the chat, yeah. Okay, so I'm skipping because we should probably wrap this up pretty soon. I'm going to be skipping union, replacement, exponentiation, and a few others, and look a bit at graphs and trying to make a suggestion what Axel's anti-foundation axiom could be. So remember that a graph, we can look at that in different ways in set theory, but one way is just to say that a graph is just a set of tuples, it's a set of pairs, and then sort of leave implicit what the set of nodes is. And that's the definition we'll use here. So an element of V is a graph if for any Z in X, then there is an A and a B such that Z is the pair AB. And because this element, this tuple structure is an embedding, this type here is actually a proposition. So there's at most one such pair of AB such that Z is that. And that means that being a graph is a proposition. But exactly what kind of graphs this is depends on the level of the structure. So here's an example of, we're going to do a few examples of graphs. But here's an example which lies at level 0, because if we do the, in set theory, we would have at most one edge between any 2 points if this was our formulation, but because we can move to level 0 here, we can now have multiplicities. So for instance, we could have this graph where we have two occurrences of the pair AC. Now I feel like there's a slide missing here, but okay. No, it comes just after. Good. So in order to formulate a foundation, remember the foundation says that every graph can be decorated with sets, so that you can have sets for each node of the graph, and such that the elementhood relation is exactly the one given by the edges of the graph. So if we formulate that in this framework, we say that an n decoration of a graph is a function, and the domain here is all of V, but it will mostly be sent, everything which is not part of the graph, so to say, will be sent to the empty set. So it's a decoration of graph, but it's a function on V, which for each X and Z has the property that set is in the decoration of X is exactly that there exists some Y such that X and Y are in the graph, which we started with, and D of Y is this set. And we truncate here because this might be an n+1 type. So in general, on level n, this will be n truncated. So for instance, the decoration of the graph we just saw would be a function which assigns to A here. So A is some set. The set with 3 elements, because there are 3 outgoing edges from A. And the first one is the empty set. That's the representation of B. And the second and third one are these 2 arrows here, which are the representations of C. And C is the singleton with the empty set because that's a representation of B, which is the only thing which C is related to in this graph. So so this extends the notion of a decoration to these graphs on higher level. And there's a difference here between the 0 decorations and the -1 decorations. So if we're talking about the 0 decoration of this graph, then A would have 2 outgoing edges, 1 for each of the arrows going out. But in the -1 decorations, things would be collapsed with respect to bisimulation. So then the A would only be associated with the one occurrence of these, because these are the same. And this gives rise to also non-well-founded sets, such as the Quine set, which would be then represented by a graph with only one node and a self-edge. So, and we can see that from the definition here, that if we put dx instead of set, this would be there exists some y in v such that there's an edge xy, and then dx dy is equal to dx, and because there's only one element there, that would be dx equals to the dx. So that will be this thing here. So we say that a structure satisfies anti-foundation if the graph has a unique n decoration for every n. Oh, sorry, not for every n. For every n, we define that n anti-foundation is that it has a unique n decoration. Every graph. Yeah. And the proposition is that what I currently have proven is that at the top level, the coiterative version satisfies the infinity anti-foundation. And the proof there is really straightforward. I'm not going to go into details here. So I'll wrap up with the conclusions. So the conclusions are that so far there seems to be natural extensions of many set theoretical axioms to higher age levels. And normal everyday notions such as graphs can spin off interesting concepts. And these two hierarchies which we constructed, they give, just like at the zero level, we have a zero type of zero types, we get an n type of n types at each level. So that might be useful. For the same reason, it's useful to have a zero type of zero types to create an unsaturated category of sets. We might want now an unsaturated category of higher structures. So that was all I wanted to say so far.
Thank you, Håkon. Let's give him a round of applause. And we're a bit short of time, but if there is any quick question or comment. Nicola?
This may be very daft, but I'm teaching graph theory at the moment. Like in everything in combinatorics, there is this terribly annoying thing about labeled versus unlabeled things, which in part can be remedied using species. But I was wondering if what you're doing with univalence could also help with that.
No, I don't think so. You run into the same problems here. Yeah, but like when choosing this notion of a graph, you have to be really careful to choose the right thing to get this anti-foundation axiom to be the right thing. So no, unfortunately.
Hello, can I say something? I'd like to point out, advertise some what one might call parallel work, another approach to generalizing set theory, which is on my webpage at paultaylor.eu/ordinals. So this is reincarnation of work I did in the 1990s, in which you get set theory with sets as co-algebras for a power set functor. So what I've developed is the theory with pretty general functors on pretty general categories, which obviously, like your work, suggests generalizations of set theories. My feeling actually is that it's I have a more flexible possible generalization, but anyway, I would suggest that you compare the two and see you know, pick up some ideas from mine and contact me with ideas from yours. Do I have a question? Well, one question was, can you give examples if you just go at one level, but in fact you have done. So good for that. You know, the reason why we generalize things in category theory, or a good reason for generalizing things in category theory, is that they turn out to be things that we already knew in some other context. Sorry, that's not a very well formulated question, but maybe that's enough remarks there for you to pick up on something.
Thank you. I will check it out. I could say that these at each level, the model will be a fixed point, not of, so at level 0, it will be the fixed point of the power set functor or power set operation. At the next level, it will be the fixed point of the covering, the type of coverings. And at the next level, it will be, well, what do you call them? 2 coverings and so on. And then at the top level, it's the fixed point of the functor, which sends just x to families over x.
Okay, so there's the link that Paul sent to everyone, and
I have a question, may I?
Yes.
So I've also taken some interest in interpreting like first order logic kind of logics in homotopy type theory, and I recognize a lot of things, but I'm curious about you use equivalences. You introduce that for extensionality in order to yes. So I'm curious if the recipe sort of for translating set theory into homotopy type theory is that we should replace the logical equivalences with homotopy type theory equivalences.
Yes.
Okay, then. So it's time to thank Håkon again. All right.